Okay, so our memory, if we go back into here, we are supposed to support three functions: write, which attempts to write data to memory; read, which attempts to read data from memory; and set state, which delivers an address, ren and when. So three different inputs. All right. This allows us, this forces us not to be able to set when or ren unless we've also provided an address for destination or source. All right. So if we think about this, then we have memory is going to keep track of a current state. So we're going to have a private when, and we can call this guy, we can make this guy a Boolean if we want. So that's effectively what it is a 0 or 1 is a true or false. So we could say Boolean when ren. And then we can also say private int address. And then we can say private string write data. All right, so in our constructor here, we'll go ahead and default these guys. So we'll say this dot when is equal to false. This dot ren is equal to false. This dot address is equal to -1, which we know will not be a legal bucket in our array. And then this dot write data is equal to the empty string. Okay, so that's what these things will be. And actually what we could do is I'm going to steal those 4 lines just in case. And I'm going to create a private void reset that just does those 4 things. And then at the beginning of memory, I'll say this dot reset. All right. Not that I'm going to necessarily use this again, but I might want to have a way of just quickly resetting all the states of the of memory. All right. So we're going to have a public void set state. Now, actually, we're going to do set state last, because set state's going to be the thing where some decision making, that's where our logic is actually going to happen. So we're going to say public void write, and this is going to take a string, I don't know, word as a parameter. Call it word data. All right. Now, all write does is it sets write data, this dot write data equal to word data. That's what it does. So if we go back to our picture here, what's happening here? We are setting this guy right here equal to a value. All right, this guy's getting set equal to a value, but that value doesn't necessarily drop in to our memory at this point. It's just waiting there at the door for the door to open so we can get through. All right. Now, what does read do? Read allows us to get at a place in memory, but we can't read, that door is locked unless we open it with our setting state. Okay, so what will read do? Public, we'll say string, read. All right, and read will only be able to read if what's true, if ren is true. So if this dot ren, then we'll return this dot the words at bucket this dot address and we need to get the data that's there. So inside of Word, we have this thing called bits. So I'll go ahead and right click and I'll generate a getter. Source, generate, and I'm going to get a, I'll actually do a getter and a setter for bits because I'm going to have to be able to write to it. Okay. Now we are actually going to come in here and doctor set bits a little bit here in a few minutes, but for right now it's fine. Okay, so memory. If this dot ren is true, we're going to return this dot the words at address dot get bits. That's what we do if we are able to successfully read. If we aren't able to successfully read, you can decide how you want to handle this. Maybe you can do a throw runtime exception. Memory fault, can't read, something like that. Or ren not set. However you want to handle, this is new runtime exception. All right, so we can try to read. When we try to read, we check from ren. If ren is true, we grab the value from the current address and return it. Otherwise, we'll scream. It was a bad read. All right, now we have a public void write, and this guy's going to get taken a string word data. Actually, didn't we already wrote write? All right, so we have a write, and all write does is it sets this global waiting area for the value we will write next. Now we're going to have set state. Public void set state, and this guy is going to take in an address, a Boolean ren, and a Boolean when. Any way you cut it, we're going to set address equal to the address that was just passed in. All right. Then we'll ask the question. Well, we'll say this dot ren is equal to ren. This dot when is equal to when. Now we're going to ask some questions about the current state of our memory. So we know that we're allowed to if we just set when, for instance, and ren is off, a write is allowed, correct? So if this dot when and not this dot ren. Remember that we can only write when reading is disabled. So if when is true and ren is false, because reading is more powerful. Under any circumstance, if ren is true, doesn't matter what when is. We cannot write. So the only situation, so this really says, can we write? The only situation where we can write is when this dot when is true and this dot ren is false. And if that's the case, what do? We set this dot what do I call it? The words at bucket this dot address equal to, I have the value that I'm going to write is what? This dot write data. All right, but that's a string. I need to set the word that lives at this address equal to that string. I do that by saying get the word dot set bits. I'm going to go ahead and pass it my string. But at this point, we're not guaranteed that that guy is the right bit width. Okay? He's a piece of data that we've written, but we don't necessarily know he's the right bit width. So I'm going to, we have this function called pad here. Here, just because I am lazy right this second, I'm just going to copy pad because it already does what I want it to do. I'll put it into Word. And we'll make this guy private. So now when I set bits, I'm going to set the bits equal to this dot pad bits and bit width. So I updated my setter for set bits to take in the string we want to write. And I'm going to go ahead and set this guy to whatever bits I have padded to this width. Now, we can make the assumption that the person's writing a binary collection here, which string bits kind of indicates we expect a binary string. All right, so that means whatever we pass this guy should be a binary string. Might be convenient for us as human beings testing this to go ahead and get the integer value of this guy for reading and writing, just so it kind of makes sense to us. So what we might do here.
What pad is this again?
Who?
Pad?
Add zeros.
Okay.
So if I have the number 3, 3 is represented as 1, 1. But if it's 8 bits, I'm going to add 6 zeros before it.
Okay.
And we already wrote pad earlier. I just grabbed it and threw it inside of this guy. I probably should have written it in some sort of utility class or something, but we didn't. Okay. So what I'm going to do is I'm going to update Word just a little bit so it's a little bit friendlier to work with. So here's my display for Word. So I'm going to display the bits, and then I'm going to concatenate onto that, maybe a little arrow like that, and then I'll concatenate onto that integer.parse int this dot bits and then 2. So this will show the binary version followed by the decimal version. All right, so in memory, when we write, I'm taking in word data here, but I might want to, from a testing perspective, I might want to write a 7 or write a 13. Make sense? Rather than me passing in a binary value. So I'll take in a, we'll call this word decimal data to kind of be explicit as to what kind of value we're expecting there. And then we're going to say integer.to binary string. Oh, that's actually going to be interesting. Here, we'll have this guy take in an int. Int word decimal data, and we'll say integer.to binary string, and we'll pass this guy the word decimal data. 2 binary string like that. All right. So we'll write the data, and the data we're going to write is going to be our binary string version of the int we passed in. This will allow us to conveniently test it. All right. Similarly, when we read, we're returning this string. So we're getting these bits. Probably we want to go ahead and return the number, the decimal number of this guy. So I'll return, here's our bits. What do I want to do with these bits? I want to turn them into a decimal number. Integer.parse int these bits, assuming they are in base 2. And then I'll concatenate it onto the empty string. That's if we want to return a string. Since we're writing an int, we can always return an int too if we want. Maybe that's just the convenient thing. These are choices. If I write to memory where I'm writing a number, I can read from memory and ultimately read a number. Okay, so now we should have a functional memory chip. We can test this. Let's go into driver. So we're going to shrink our memory down a little bit to size 10. A couple smaller buckets, right? All right. And then if I go ahead and run this right now, I should have a bunch of 8-bit width values with a 0 on the end, because all these numbers transfer to a 0, right? 0, 0, 0, 0, 0, 0 is a 0 in decimal. So now we'll go ahead, we're going to say m.write. And I'm going to try to write a 5. If I print out memory, is memory going to be any different? Did a write actually occur yet? No. I've notified memory of my intent to write a value. What I've done here is I've delivered a, was it a 5 that I was trying to put in there? 5. I've delivered a 5 right here. But it's not written yet. The only way it can write is for me to say where I'm going to write it and then give it the proper flags for when and when. Make sense? So I say maybe I want to put this at bucket 1. My address is 1. And I want, if I want to write it, I need ren to be false. And I need when to be true. So now I'll say m.setState. And I'll say I'm going to write this guy, pick your favorite bucket between 0 and 9. Because that's how many I have here, because I have 10 buckets of memory. And we're going to set ren equal to false. And we're going to set when equal to true. At that point in time, a write actually occurs. That makes sense? So now if I display, we should see bucket 2 is equal to a 5. There's bucket 2 equal to a 5. Make sense? Now, at this point in time, my ren is still a 1, and my ren is still a false, and my when is still a true. Now, if I want to read something, let's say I want to read from bucket 2. If I want to read from bucket 2, if I just go and do this, if I say m.read, I already have my address set to 2, right? So I've already notified it where I want to read from. So this is going to attempt to read from this memory chip. But is it going to work? Is my memory currently in a state that it can read? Read enabled is false, write enabled is true. Can I read from this memory chip right now? Cannot. So it's going to give me a runtime error. Runtime exception, memory fault, ren not set. If I want to be able to read from that guy, I have to set state. I'll tell it, where do I want to read from? Let's say I want to read from 2 because that's where my value is, right? So I'll read from 2. And I want to set ren to true. Now, truth be told, I can set when to whatever I want it to be. True or false, it doesn't matter. Why doesn't it matter? If I set ren to true, why does it not matter what when is?
Because read is more power than.
Yeah, read's a higher priority.
Yeah.
Read is higher priority than write. So as soon as I say true for ren, it does not matter what I put in here for when. It will never be good enough to override the read. Having said that, since I'm setting the state directly, I would probably do this. Set false, I'm not writing. But consider this in actual digital logic, where you might have signals all wired together, where you might still have a 1 being delivered to when. And that's not necessarily a problem, as long as a 1 does get delivered to ren. Because ren is always going to take precedent over whatever when is. So we have electricity flowing through all this stuff, and we might have some switch or decoder or something like that down here that ultimately is sending a signal to the when portion. We'll see that with the composite chips here in a few minutes. We don't have to disable that to do a read. We just have to deliver positive flow to the read enable in order to do a read. Make sense? But since we're having direct control of it right here, we're going to set read enable to true and write enable to false, because that's effectively what we're doing. And then I will try to read here, and it will successfully read this time, but I'm not actually displaying the value. So if I want to display the value, I would say system.out.println m.read. And now I should have successfully gotten my 5 that I read. And we can test our priority thing here by going ahead and saying, hey, I didn't know any better. We'll go ahead and write enable as well. But since read enable is more powerful, our read will still be successful. That make sense? All right, so now if we want to, okay, here, this will be a good test. So now I'll say m.write 8. What will this line output? Not blade. Given those instructions, what will that last line output?
I'm not around.
Huh? And what is in bucket 2?
5.
Why is it still a 5?
Because you did not. Because you're just sending 8. You're not really allowing it yet or doing anything with the when or ran after that, right? You're not ever.
Okay, so I'm attempting to write here.
Yeah.
That's setting it, trying to set it to an 8. This will show me the 5 that's still there because ren always takes precedence. There's my 5. Now I can set state right after this because I have delivered my intention to write an 8. Have I not?
Mm-hmm.
So I can set state to maybe a 4. memory address 4 and say that I want to write to memory address 4. And then if we do a display here, we should see a 5 in bucket 2 and an 8 in bucket 4, followed by a runtime error. There's the 5. There's our 8. Why did I get a runtime error? Because I'm not currently allowed to read, because read enable is off. So now I can set state true and whatever makes us happy. And now we'll be able to read the 8. That make sense? That's how memory works. A single memory chip works that way. Okay. So questions about number 2?
Can you go back to top?
Is that good? What's the next one? So in similar way to question 2, write a class called Composite Memory, horizontal. So we're mimicking 6.3.1, which maintains an array of memory objects from question 2 above, and supports the same read, write, and set state functions described in number 2 above, and gives the appropriate results for an on-state change. Note that this allows us to store larger values since we get more bits for a single write, as opposed to vertical, which allows us to store more values because we get the same size of values, we just get more of them. All right. So let's, and this is 6.3.1 that we're mimicking here. All right, so composing memory. What does this mean? This comes down to what this chapter was talking about in terms of cost of memory. We've had the discussion, I think, in here about how expensive memory used to be, but we've talked about it in several of my classes before. Memory used to be really expensive. It's a lot cheaper now, but it used to be really expensive. So the idea of being able to mass produce one object a zillion times tends to drive the cost of that single object down, right?
Yep.
All right, so one of the chapters in this book, I think, was about the economics of memory or something like that. And I'm guessing it said something about a single custom chip, super expensive, a whole bunch of the same chips, less expensive.
The design is very expensive.
Well, in general, the design of anything is very expensive. But if you design something once and then make it a million times, that's going to cost less than making a million unique objects, a million unique designs. Okay? So it might be in our best interest from a cost-saving perspective to design memory once, like we just did, right? We've now designed memory. We have a Java object called memory that mimics memory. We can design it once, and then we can link a whole bunch of those guys together to give us more storage ability. Either the ability to store more things or the ability to store bigger things. Make some sense? So here's our example of composing, in this case, 2 memory chips horizontally into memory with twice as many bits per location. So our location is address 0, address 1, address 2. That's our place in memory. If we're doing these guys horizontally, the left 8 bits, although it's probably in little endian, right? So the right 8 bits are actually the first 8 bits. That would make sense. I don't know if that's the...
I think it just concatenate.
No, interesting. In practice, more than likely, this is written in, this would be designed using what we've talked about before, the little endian, where you would store the priority order of bits from right to left. So kind of like bucket 0, bucket 1, bucket 2.
But that's it graphically.
Well, we say graphically, yes, but even as you read from it, you have access points into memory, like where your array begins. So depending on how the chip is built, you might do that, but little endian is a pretty common way of doing anything architecturally. Okay. Yeah, no, this is right. It is. But bits 0 through 7 are here, but bits 8 through 15 are here.
It's just the right in the reverse order.
Yeah, I get it. I'm just saying that the architecture they're showing here does show a little endian storage architecture, where the far right is the smallest, least significant bits. The far left is the more significant bits. When usually when we write a number, 127, the left is our, well, actually, I guess we would write it the same way. 127, the left is our most significant bits. All right, so each one of these guys here is one of the things we just built. All right, so we have to have them linked together somehow. So what we do is if I have 2 8-bit width memory chips linked together, when I write something, I can write up to 16 bits. That make sense?
Yep.
And what do? I split those 16 bits into 2 pieces. Bits 0 through 7, I put on one of the chips. Bits 8 through 15, I put on the other chip. So a write comes into composite memory, and then composite memory holds a collection of memory chips organized. Remember, this class is called Computer Organization and Architecture. So organized in a horizontal pattern here, which says we will split the data between the left and the right. Or really, we're splitting the data between all of the memory chips that are going into this composite memory. All right, so we're going to build an object here for composite memory, and then we'll come back to this. So I'll right-click. We'll say New Class. And we'll say Composite Memory. All right. And we're going to say the composite memory is going to hold a collection of memory. So I'm actually going to say private Boolean
You said making 2 classes, so
Oh, did I say 2 classes? Did I say composite memory horizontal?
Yeah.
So you're not doing this way.
Fine.
Well, it's easier to...
Composite memory horizontal. I don't know, whoever gave you this homework assignment really painted it by number for you. All right, composite memory horizontal, that's what we're doing first, right? Is composite memory horizontal. Okay, good. So this guy is going to hold a collection of memory, and we're presuming the memory is going to be organized horizontally. So this guy's going to operate as horizontal memory. All right, so what we'd probably do is we'd have we're going to have a private memory array. called, what do you think I'm going to name this guy, Maddie?
The memory.
Oh, I have to call it the memories?
That's what I called mine.
I'm down. All right. I would have called it the memory.
Why'd you ask me?
I thought you were like a step ahead of me because didn't you say, you answered that last class saying something like
Yeah, I did.
the buckets, right? Although, given that, given that, why would I call it, if I had an array of buckets, why would I call it the buckets? When in this case, I would have called this guy the memory, not the memories. It seems like it's
You chose the name, Maddie didn't.
I know, I get it. So, but I'm telling you that I would call an array of buckets, I'd call that the buckets. But I would call an array of memory objects the memory.
Because bucket is indeed splitted bucket, but the memory treating multiple memory together.
No, I don't think that's why though. I'm just telling you what I'm naturally coming up with here. I really think this is an aunt versus ant question.
Yeah. No, I think
It just sounds right. I mean, we had that discussion, right? About whether somebody is your aunt something or your aunt something, and it depends on the person's name.
You?
I asked the same question, but
Because it's like, I have an Aunt Beth, but I have an Aunt Rhonda.
because Aunt Rhonda doesn't sound right.
Yeah, it doesn't sound right.
Yeah.
See, I'm kind of buying it. Yeah, no, hey, look, you and I are in the same place, but now I've switched over to Team Maddie and Ani. I'm sold on this because my naming conventions seem to support this logic.
You betrayed us.
With buckets, you just add an X, but memories, you have to change the whole Y to IES, so it's probably just easier for you to do memory.
So now I'm back. Which team are you on?
That's true.
I don't know.
Aunt or aunt? Are you?
Team Jordan.
I don't.
You just say aunt for everything?
Yeah.
All right, I'm back on Team Jordan. She gave me an explanation for this. Is I had to actually change the stuff.
I mean, that's why
But
I always thought aunt
But I
was
have a
like
counter
English
argument. You don't spell anything right, so I spell this right.
I really can't argue with that. In every one of my classes, I don't really need a syntax helper. I need a spelling. I need a spell checker. Why is that?
You just don't care.
Yeah, I mean, it's like I got my hand shake too much, so I miss keys. But yeah, a lot of times I don't care. I think you're right. These keys just get in the way. Wish I could just think. If I could just think what I wanted to go in there, that would be so much easier. That's what Mr. Gonzalez does. He doesn't even open his laptop when he codes.
We wouldn't need coding if that were true.
Huh?
We wouldn't need coding if that were true.
You could if you just thought the syntax. All right, I named mine the memory. That's what you named yours, right, Jordan? Yeah, see, Team Jordan. All right, so private memory, the memory. And this is going to be public composite memory horizontal. And we probably could take in maybe a number of chips. So like int num chips, num mem chips. All right, so then we'll say this dot the memory is equal to new memory array of size num mem chips. Now, we probably also, if we just want to be consistent here, we probably want to go ahead and take in num mem chips as well as the number of cells and the number of bits per cell, because that's going to be a driving force for this guy. So if we go back to our memory here and we look at the constructor, we took in num words and we took in bit width. All right, so we have our num mem chips. That's how many individual chips we're going to have. And then what will each chip look like? It will be this many words, this many bit widths. Okay? So we're going to create a new memory array here. I used parentheses instead of square brackets. So there's my memory array. Now we're going to fill it up with this many memory chips of size num words and bit width. So for int I is equal to 0, I is less than this dot the memory dot length, I plus plus this dot the memory at bucket I is equal to a new memory, passing it num words and passing it bit width. Okay. So far, so good. All right.
You call the number of memory chips, but it's the memory.
Num mem chips. Yeah, I can't. At this point, I really can't explain it.
Your naming conventions keep on.
They're perfect. The naming conventions are perfect.
Perfect.
All right, where's my picture? Okay, so we'll go back to this guy. So now I've created an object which encapsulates this idea of a composite memory, horizontal composite memory, right? So I have an object that stores in it an array of memory objects where this is at bucket 0. Well, actually, this is at bucket 0. This is at bucket 1, whatever. And we want to have the same things that we had for regular memory set for this guy. So we want to be able to write something, write data, but that data is going to be equal to a bit width. Here, let's go back to here. Each data that I write to horizontal memory is going to be, give me the generic, in terms of the variables in here, generically speaking, how big will each piece of data I write be? So in this case here, I have 2 memory chips. My data size is 16, right? Because each memory chip has a bit width of 8. 8 times 2 is 16. So over here, what will the size of my data be that I write, generically speaking?
Number of chips times bit width.
Yep. So this guy, the number of memory chips I have, times the size of data per memory chip. Because I'm splitting my data up across these horizontally organized memory chips. Make sense? So if I have one piece of data and I have 3 memory chips, I'm splitting that data across those 3 memory chips. So in this case, I'd have 24 bits. So we're going to go ahead and we're going to say private int data bit width. And we're going to set this dot data bit width equal to num mem chips times bit width. So now I've stored the width of each data chunk, let's say, that might get written to this memory. That make sense?
Yep.
So now, similar to what I had in memory, I have some booleans for when and ren. I have an address. I have my write data.
You probably all need.
I won't need the words. The words is actually encapsulated inside of each of my memory things. Yep. Okay, so I have the same when and ren that gets split across all the guys, right? I have my address that I want to read or write from, and then I have the data that I'm going to write. And that data will always be of size data bit width. Okay, you know what here? I'm going to need to pad here as well. So I'm going to, where's pad? Pad. Oh, is it in Word? don't suck helper. So we're going to have a class called don't suck helper, and this guy is going to have a static, public static pad. So then whenever I need this guy, I won't call this .pad, I'll call don't suck helper.pad. This is my one function that I wrote that knows how to pad bits to a bit width. Similarly, I'll do that out here in driver, even though I have it commented out right now. Oh, I still have my pad out here, so I'll just delete pad from my driver as well, which will give me an error somewhere. Right here. Don't suck helper.pad. So I've written my pad function now one time, and I can call it from multiple places. All right. Laziness can explain why I wrote it twice in the first place, but if I'm going to write this thing 3 times, that can't stand. So we put it in one place, and we can call it from those places.
And the laziness can also explain why you put it in one place.
Which thing?
I say laziness can explain everything.
Yeah, but I think I could be lazy enough to rewrite the same method twice out of just boredom.
But laziness make you don't write the third time.
Yeah, but the third time starts becoming something that offends me. That's just bad programming practice, and that can't stand. Yeah, so I even punished myself by naming the class don't suck helper. All right, so this is going to be my class that has some of my utility functions that are shared across my my things here. Okay. All right, so we're going to need to have similar things to what we had before. We're going to have our write, correct? Now, in memory, did I pad on the write? Because I wrote a decimal, right? So here, we will just steal this. So for composite memory, when I write, I will write a decimal data, and I'll go ahead and set that guy equal to whatever's there. I'm not padding yet, because I'm not actually doing the writing yet. Make sense? Okay. I could pad if I wanted to, but if we're mimicking this right after our memory, on set state, if we were writing, this is where we set the bits. Oh, we set the bits inside of our
Memory.
Ooh, this is gonna start getting spicy. All right, because we actually have that guy pad the bits. So inside of a word, we set bits, and this is the guy that sets the bit width. Okay, interesting. Well, we'll address that in a second. We're going to probably have to change the way this works a little bit. So rather than pad inside of set bits here, we're going to pad before that to make sure it's the right width. Yeah. So I'm going to set this guy equal to bits. This was the original setter that it had created for us without any modification. And then what I'll do is in here for memory, when we do a write, I get my binary string, I'll go ahead and pad it because I also am keeping track of, well, I don't keep track of my bit width. I am now, so I'm going to keep track of int bit width. That way, when I do a write, I know how many bits that write should be. So memory is going to know about its bit width. So when I do a write, I'll set write data equal to the binary string, and then I'll update it. Write data is equal to don't suck helper dot pad this dot write data, and the number of bits is this dot bit width. So now I'm pre-padding it rather than relying on a word to add the extra bits to it. That makes it now compatible with my composite memory when I go and have to take 16 bits and write 8 of those bits to one guy and 8 of those bits to another guy. Make sense?
Mm-hmm.
Otherwise, my words would have padded out. I could have made it work by always making sure I delivered it the right number of bits, so I probably didn't need to make this change, but I think this is better. Okay. So that's what my write looks like here. I'm going to go ahead and steal that from my composite memory because we started writing this. So my write for composite memory is going to take in the decimal data. I'll go ahead and set my write data equal to that, and then I'll pad that to, what did I call it? I called it data bit width. I don't know why I called it something different. We'll just call it bit width, just so it matches. All right. So now, in our example here, when I write a 7, we go back to the picture here. If I were to write a 7 here, it would now prepare to write a 16-bit version of a 7 rather than an 8-bit version of a 7 in the example where we were writing to just one memory chip. Nothing's been written yet. I'm just preparing to write. Make sense? Yeah. Okie dokie. So that's my write. Now, my read. Go to memory. Take that guy. Now we probably could write this with like interfaces or some sort of generic class that we inherited from, since we have the same functions in there, but we'll cough it up to laziness for the first thing, and then we'll fix it if we run into a second thing. So read is going to say, hey, if my read enable is on, then I'll go ahead and it's not so simple anymore, right? Because if I'm reading from this guy, I have to reassemble my bits, because my bits are now split across all my memory. Make sense? So I need to reassemble bits for the read. So I'm going to ask each word to give me its value at that location. And a word, we have a get bits that just gives me the bits. And we are building this from right to left. So my smallest bits are over here, largest bits are over here. All right, so where am I here? Here. Composite memory. So we're going to reassemble the bits. So I'm going to say string the bits. Starts off as the empty string. And I'm going to say for int I, actually we can say for word W in this dot. Oh, yeah. It won't be word, it would be memory M in this dot the memory. So I'll go through each memory chip that I have, and for each memory chip I want to get the bit, I want to read from, so this is actually going to give me the because I can't ask a memory chip for the bits. Read gives me a very specific thing here.
I think you have to return the word, the bits. Otherwise, return the bits.
Yeah, but what fun is that? That's not how our chip works.
I think read returns the word.
Well, not right now.
That is not your chip. It's not.
Well, our chip is better. Our chip returns an int. Doesn't pay any attention to the number of bits. Yeah, that's okay.
Or you can
We'll work with it. It's insignificant. It doesn't matter. So what we're going to do is from this memory, we're going to do a m.read, and this is going to give us an int.
Yeah. Then you convert it into binary.
So int val, we'll say val is equal to that memory chip dot read. Now that guy is currently in a, he needs to be converted to a number of bits equal to bit width divided by the memory dot length.
Yeah.
That's the number of chips I have. So if I have 2 chips and my bit width is 16, 16 divided by 2 is 8, I need the 8-bit version of this number I just read.
Yeah.
So I'll say the bits plus equals don't suck helper dot pad. The binary number I'm going to do here is an integer dot parse, integer dot to binary string val, and number of bits is going to be here I can actually do int bit count is going to be equal to this dot bit width divided by this dot the memory dot length.
Doesn't your memory has the bit width?
Oh, it does. But do I have a getter for it?
Well, I just want to say, like, the check if it has it.
I do have bit width.
I think it's
Do I-
easier to say get from.
Yeah, it is. So we'll ask each memory chip, even though it's always the same.
How is it, if it's not the same, it will be really complicated.
Well, it wouldn't be usable memory. Memory relies on horizontal and vertical memory relies on it being the same size.
But if we say, I would say get from each memory is better than having average, because in that case you will be.
Oh, probably true. Yeah. So I'll add a getter for bit width. So I can ask the individual memory what his bit width is, which would be the exact same value as we are calculating right here. This bit count, it would be the same value.
You can say the first memory of the.
Well, we might as well just use the bits here. So m dot
Here you can.
get bit width.
This is better.
I don't know about better. It's fine. This
And
reads better.
Here you cannot using plus and equal to, because it's built in from right to left. You should be say the bit equals to this thing plus the bit.
Oh, that's what plus equals does.
No, I say it should be.
You want to build it backwards. So we're doing this plus the bits. Instead of the bits plus equals says,
It should be bit plus the.
you want to say this, the bits concatenate with that?
Yeah.
That's what plus equals does.
Really?
Yep.
I don't think so. Plus, if you say one plus equals to 2, does it getting
There.
1 2 or is it getting 2 1?
Here, we'll say int a is equal to 5. A plus equals 7 is the same thing as saying a is equal to a plus 7.
But string concatenate is different because
No, not the operator. Plus equals operator is the same.
because the newer thing should be in the left side.
I understand what it should be, but if I say the bits is equal to the bits plus this don't suck thing,
I'm doing right vice versa. So sorry, it should be. Okay, let's.
those two lines are identical to each other.
Yeah, you're right.
The bits plus
Yeah.
equals is the same as this guy here.
Yeah, true.
And because we're going through, so I'll get my first value, which would be the far right But then I'm going to put the next
In
value
the left.
to the left of it. Yeah. Well, no, it'll be to the right of it. I am building it backwards. So this is actually incorrect. So this would set the bits equal to my first number. Let's look at the picture here. Since this is bucket 0, this is bucket 1, this would set my bits equal to this, and then the next time through, I would take this value, and I would concatenate this onto the end of it. But I actually want it the other way around. Yeah.
So that's why I say that plus equal to is wrong.
So why are you creating two chips again? The two memory chips?
Because that's what composite memory is.
But where are you creating on the
In our constructor for composite memory, we tell it how many memory chips.
Okay.
Yeah, so this would be building our bits backwards.
Yeah.
Both of these lines, so for starters here, both of these lines right now do identical things. They just do the identically backwards thing.
Yeah, but it's wrong.
So we need to take this and concatenate it onto the end of that.
Yeah.
That way we're building our string in reverse.
Yes. I only remember because in my experience it's wrong, but
should be
I don't
okay.
really remember why it's wrong.
So we're going to go through all of our memory. For each memory, we'll read the value. This is going to come in as an int. Then we'll pad that integer to the right bit width, and then we'll tack it on to our bits in reverse. So effectively what we're doing is we are collecting all of our bits from all of our memory chips and reassembling them into an example of 2 chips, 16 bits, 3 chips, 24 bits, 4 chips, 32 bits, so on and so forth, right? So whether if it's the number 7, it's going to be the 16-bit version of 7, or the 24-bit version of 7, or the 32-bit version of 7, or the 64-bit version of 7, yada, yada, yada. There's going to be a lot of zeros. You can store very small values in a lot of bits, and you're just going to have a lot of padded zeros. Okay? Because remember, horizontal memory allows us to store larger bit spaces. Now, by having more bit spaces, in order to store a value in a certain memory location that is 16 bits instead of 8, what does that let me do? Why would I ever want that? Why would I want to be able to store 16 bits at a single place in memory rather than 8 bits at a single place in memory?
You can store a larger number.
Yeah, bigger stuff. Why would I want to store 64 bits? Even bigger stuff. 128 bits. Even bigger stuff. Well, why don't we always want bigger stuff? Well, I think it's just as fast.
Floating number will be more precise.
Well, that's the opposite question. Why don't I always want bigger?
Depends on your needs. If you don't need it.
Well, so in normal programming, what's the biggest number you use?
5,000.
Billion?
A billion?
Yeah, normally no.
Okay, so that'll fit in an int, right?
Yeah.
So 32 bits is really probably plenty for most of the things we do. That's why when we program, almost always the numeric type we use is int.
Yeah.
It's big enough. So we actually, from an operating system perspective, only need a 32-bit memory system in order to store 32-bit values. Make sense? Well, I might never need more than a 32-bit value.
There's one thing, memory address will easily exceeding that.
So, we have 2 sides to that. So on one hand, we have what's the biggest size of a value we can fit in a bucket, right? We've designed our little chips here to hold 8 bits in a single bucket. Now we link a couple of these chips together. Now we can hold 16 bits. If we link 4 of these chips together, we can now store 32 bits. Now we're saying, under general circumstances, 32 bits is enough for us, correct? That seems reasonable. 64 bits is, that exists. We've heard of 64-bit values, but have we heard of 128-bit values in normal programming? Where's the only case we hear about 128-bit or 256-bit values? We've heard of 128-bit this and 256-bit this What's the area of computer science where we would,
Encrypt.
yeah, cryptography. We have 128-bit private keys, 256-bit private keys. Why do we want bigger bits on private keys? Not Blade, somebody else. Why do we want bigger bits on private keys? What's the private key in encryption? Encryption. What's the private? Make toast, French toast. We're over time too. So let me just ask this last question, and then we'll take a break. So, what's our private key in cryptography? What do we use that for? It's our password, right? So, what's better about a 128-bit private key than a 64-bit private key? Yeah, safer, harder to crack, right? So if we think about that, 128 bits is a whole bunch of zeros and ones. If we think about if we do our password as a ASCII thing, so that would be divide that by 8. How many of you have a common password that is 16 characters long? Yeah, the password that you type. You know how we have our go-to password? So 16 bits. Okay, well, I mean, and that's good. I mean, that's actually impressive.
Mine's 15.
Whatever. Well, see, now we've narrowed it down. We know we now have a target. We can generate every 15-character password.
She is more vulnerable.
Okay, but so the point is that now if we jump to 256 bits, that's 32 characters long. Wouldn't that be a lot harder password to guess? Because that's 32 characters mixed between upper, lowercase, and punctuation. So how many permutations are there of 128 characters? 128.
No,
I'm sorry.
my password.
28 characters? That's a sentence.
It is a sentence.
It's called a passphrase. That's not a password.
It's safe.
Huh?
It's safe though.
Well, yeah, I mean, I'm not even making fun of you. It's actually called a passphrase, not a password. I mean, it's a real thing.
Would you consider 15 a passphrase? Because Northwestern Mutual, they require you to have 15, but they've been kind of calling it like, I don't know.
It doesn't necessarily matter.
Yeah.
But if we do this, so we have 16 characters times each character can be what? So we have 26 times 26 times, I don't know, maybe like 10 punctuation options or something like that. So each of those 16 characters can be 6,760.
You're forgetting numbers.
I am forgetting numbers. Well, no, I actually didn't forget numbers. I have them in there now with the 10. So then we'll throw another 10 for punctuation. All right, so each individual character can be one of those. Right? And they can be in any order. So it's factorial for the number of permutations. It's a lot of password guessing. Okay, so more bits, more secure. But for storing numbers, we don't need that. All right, so let's take 10 minutes, 12 minutes, 10 minutes, 10 minutes. 43.